Okay, this video is about how to understand, how to get your head around enthalpy changes and these definitions. So you've got a few definitions to learn for year 13, and some of you will find it difficult to just learn them as I've asked. So I want to put them in a bit of context and explain some of these enthalpy changes to you. So the first thing to realise is that all of these definitions start with the same sentence starter, which is the enthalpy change when 1 mole of. So all of these enthalpy changes are defined per mole because they're going to be in kilojoules per mole. So that's why they start off with the enthalpy change when 1 mole of. So if I start you off then, if we did the ones from last year, delta H formation is the enthalpy change when 1 mole of a substance, so for example NaCl solid, is formed from its constituent elements in their standard states. So I know I did this one on a video yesterday. Constituent element is sodium, constituent element is chlorine, standard state of chlorine is Cl2 because it goes around in pairs and it's a gas. And that is the enthalpy of formation. It's the enthalpy change when 1 mole of, and then you've got to learn the end bit. So you don't need to learn this bit. 1 mole of a substance is formed, and there's the clue there from formation, from its constituent elements in their standard states with everything under standard conditions. Delta H combustion is the enthalpy change when 1 mole of a substance is burned completely in oxygen. So this time it's referring to a substance over this side, which might be carbon. That's the 1 mole of carbon being burned. So that this carbon is the subject of the enthalpy change when 1 mole of, but it's still 1 mole of a substance being combusted. So the clue, formation, tells you that you're making the thing. That's what you're making, 1 mole of this substance. You're burning a substance, so it's going to be over this side. All right, so if I look at some of the ones that we introduced yesterday, and I've asked you to learn for next week. I've got my sheet here somewhere, my definition sheet. I'm a pro. I'm literally making a video on this and I can't find the definition sheet. Right, so here are the two there. Enthalpy change when 1 mole of a substance, the enthalpy change when 1 mole of a substance. Ionization energy is the enthalpy change when 1 mole of, look there, is the enthalpy change when 1 mole of gaseous atoms loses an electron. So when 1 mole of gaseous atoms gains an electron. So then we've gone on to some more difficult ones, or some new ones. They're not actually more difficult, but this one takes a little bit of thought, the enthalpy of atomization. Now this, it says here, is the enthalpy change when 1 mole of, so there's the starter, gaseous atoms is produced from an element in its normal state. So gaseous atoms. So I'm going to look at this one now, delta H atomization, and this one needs some care. So, because it depends on the element that you're using. So atomization is when 1 mole of gaseous atoms is produced. So I'm going to do some examples. If somebody says to you, write an equation for the atomization of sodium. So the definition says the enthalpy change when 1 mole of gaseous atoms is produced from the element in its standard state. So if somebody says sodium, you go, well, produced, gaseous atoms is produced. So I would start off by writing sodium gas. So it's going to be atoms, so you're not allowed any small numbers on this side. They are sodium atoms, they're gaseous atoms, so that's fixed. You've then all you've got to do is think about what sodium in its standard state is, and sodium in its standard state is sodium solid. That equation represents the atomization of sodium. It's solid sodium turning into gaseous sodium. 1 mole of gaseous atoms produced from the element in its standard state. All right, a little picture of that. It just means some solid sodium atoms. Na, Na, Na. Wish I hadn't have started this. Na, Na, Na. You've got to put some energy in to break these apart, and you're going to produce Na gas. I hope you realise that this is going to be endothermic because you're going to have to put energy indo to break these bonds to turn something from a solid to a gas. Alright, so you get the idea, 1 mole of gaseous atoms produced. So if somebody says write the atomization for magnesium, you do the same. Magnesium, gaseous atoms being produced, 1 mole of, you're not allowed to put any numbers in front of that. You think magnesium in its standard state, magnesium, solid. So it's that simple with metals. Here's another one, mercury, Hg. Now Hg is gaseous, but mercury in its standard state is Hg liquid. So 1 mole of gaseous atoms produced from mercury liquid in this case, but it's still, that represents the atomization of mercury. Alright, just got to watch out for that state symbol, so you need to know a little bit about which elements are solid, liquids and gases. So for metals, it's very, very straightforward. All you're doing is you're changing the state symbol typically from solid to gas, but watch out for mercury. Atomization for non-metals is a little bit more tricky to think of, but hopefully not in a minute when you see this. So if somebody asks you for the delta H atomization for chlorine, well, the atomization is, so firstly you say to yourself, it's the enthalpy change when 1 mole of a substance, gaseous atoms are produced. So if somebody asks you for the atomization of chlorine, Cl2, the first thing you do is you draw 1 mole of gaseous atoms. So gaseous atoms is Cl, not Cl2, because Cl2 is a molecule. So this side you draw gaseous atoms, just Cl on its own, the symbol with a G. Then you've got to think of the element in its standard state. Well, the standard state of chlorine is Cl2 and Cl2 gas. So the atomization of chlorine looks like this. So this is not balanced yet, but you have to put a half there. You're not allowed to put a 2 in front of the chlorine because that would not be forming 1 mole of gaseous atoms. So the atomization of chlorine looks like this. 1 mole of gaseous atoms being produced from the elements in its standard state. So you think again, bromine. Right, bromine is Br2, liquid in its standard state. If somebody asks you for the atomization, you just firstly go 1 mole of gaseous atoms formed from its element in the standard state, which is Br2 liquid, and there's going to be half of them. Alright, so what we're representing here, it looks like you've got half a mole of Br2. That doesn't mean half of a Br2, that means half a mole of them. Alright, so you've got Br2s over this side, half a mole of them. Alright, and over this side you've got gaseous atoms whizzing around. So in this process it looks like you're changing the state and you're breaking bonds. Anyway, it's going to be endothermic because you're going to have to put energy indo to break this bond and then to turn it into a gas. So if you think about the process that's happening, I look at this one, it looks like I've got molecules over this side and atoms this side, you're going to be breaking bonds, it's endothermic. If you want to atomize something, you've got to put energy indo. Right? And if you look on here, it's endothermic because you've got to break bonds. You might have heard it on science fiction things. I'm going like a robot go, oh god, it's awful, this, I don't know what I'm going, it's going, I'm going to atomize you. It means he's going to break you into bits, doesn't it? It means he's going to zap you with a laser. And to do that, you're going to have to put energy indo. Sorry for that little digression there. Don't know where that came from. But if you're going to atomize something, you're going to blast it apart into atoms, aren't you? Individual atoms, not molecules. So the rules for atomization is there are no small numbers allowed over here. I don't want any molecules being drawn here. And there are no big numbers allowed over here because you're forming 1 mole of atoms. Alright, so watch out for atomization. It looks like this for metals, just a change of state symbol. But for non-metals, you need a little bit more thought because non-metals often go round in pairs. If somebody asks you for the atomization of phosphorus, for example, phosphorus gas, there's 1 mole of gaseous atoms. That comes from P4, so you would need a quarter of P4, a quarter of a mole of P4. Phosphorus is a solid. That would be the atomization of phosphorus. Because you're not allowed to put a 4 in front of the P to make it balance because you're making 1 mole of. Alright, So that's atomization. And it's an endothermic process because typically you're breaking bonds apart and you're turning things into gas. That's my fingers doing gas. All right. The next one to look at on the sheet is hydration enthalpy. Now we do a little bit more on hydration enthalpy soon. Is there oh, hang on, might be somebody at the door. Right, lost my chain of thought there. I'm doing year 10 interviews here, so somebody came in. Now, where was I? I think I was talking about the next one, which is hydration enthalpy. So, hydration enthalpy is an interesting one, and enthalpy of solution. These are enthalpy changes that we're going to look at in a bit more detail in the next couple of lessons. But let's have a little look at it. Hydration enthalpy is when 1 mole of gaseous ions become hydrated. So hydrated, it means, so you take gaseous ions, so if you've got magnesium, 1 mole of gaseous ions, so this is the subject of it, becoming hydrated means that they then become aqueous ions. All right? Now you can write plus AQ, which is just a way of saying that you're going to put it in water, but you don't have to put H2O in and worry about balancing it. That's what this means, because if you put plus H2O, you're then going to have to worry about the H2O over here. So all we're saying is gaseous ions being put in water, becoming aqueous ions. It's quite a strange sort of idea. Imagine you've got a gaseous ion flying around and you've got a beaker of water, and all you're going to do is put that in there, and what happens is you end up with a magnesium ion, Mg2+, that's what that says there, surrounded by water, and I'm going to just put that in there for now, because that's a real diagram that we'll talk about later. These are water molecules. All right, so if you look at hydration enthalpies, if you're interested in this, you can look it up and look further ahead in the booklet. So that's what hydration enthalpy is. The enthalpy change when 1 mole of gaseous ions becomes hydrated, so it becomes aqueous ions. The next one, which sounds similar, but it's different, is the enthalpy of solution, which is ionic specific. It's about ionic. So the enthalpy change when 1 mole of an ionic solid dissolves in an amount of water. So let's just choose an ionic solid. What was I going to write then? MgCl2. I know it's an ionic solid because it's a metal and a non-metal. Ionic solid. So 1 mole of an ionic solid. I'm circling the thing that it's 1 mole of. Then it says dissolves in an amount of water large enough so that the dissolved ions are well separated and do not interact. Now that's important. What it means is you're taking an ionic solid, which looks like this, plus minus, MC Bockle. You're dissolving it in water, so we write plus AQ, and then it becomes the hydrated ions. So it's similar to the one above. So magnesium chloride is made of Mg2+, so they're now surrounded by water, and chloride ions are Cl minuses, aqueous, and there's going to be 2 of them. Okay, I'm allowed to put a 2 over this side because it's 1 mole of ionic solid being dissolved in water. So what you've got to know the formula of the ionic solid and then know the charges on the ions to do that one. So what this means is you take an ionic solid, maybe like some salt on the table, some kitchen salt, table salt, you dissolve it in water and you make a beaker full of Mg2+ ions and Cl- ions. This bit of the definition that says, in an amount of water large enough so the dissolved ions are well separated and do not interact. Right, if you imagine that you dissolve an ionic solid in a small amount of water like this, you can see that the ions are close to each other and they'll probably be attracted to each other. So you have to learn this bit of the definition that you need to have added enough water so that the ions are well separated, so they're not tempted to join back together. All right. So it's a bit of a technical one to remember. This represents delta H of solution. It's the enthalpy change when 1 mole of an ionic solid is dissolved in water to form, what's it say? In an amount of water large enough so the dissolved ions are well separated and do not interact. All right. I'm going to go back just for a sec to this hydration enthalpy one. And whether this is exothermic or endothermic. All right, if you put an ion into water, what it does, it starts to form interactions with the water. So it starts to form interactions, which we're going to call bonds for now, or attractions. If it's forming bonds or forming attractions, that means that it's going to be exothermic, because bonds are forming or attractions are forming. Alright, so you can see there, exothermic. When bonds are formed or attractions are formed, it gives out heat. If you're breaking bonds, it takes in heat.